anything that's too complicated. Some of the topics we get into maybe we're going to get into the basics of what is the nature of knowledge. So the really abstract ones we may push off to the end. So there are three components I want to talk about today: semantics, deep learning, and the transformation of business. And all three of these are huge topics right now, and I think they interrelate in a way that's really big. The kind of flow of the talk I'd like to do is to start with what the economic impact of these technologies is, talk a little bit about deep learning, and then give some historical context, because things are happening really rapidly right now, and so understanding where things came from I think is helpful. Particularly, there's a distinction that they used to make, not many people make it now, between the neats and the scruffies. And I'll talk about what that is. And then finally about the nature of semantics, or meaning, and how can our technology or software have meaning, particularly for artificial intelligence systems, and then the future, where is this all going? So McKinsey recently did a report where they looked at the 12 top technologies for the next 10 years and analyzed what's the likely size of it. And if you look at it, 5 of them are AI and robotics related, and the total value created over the next 10 years of these 5 technologies is estimated to be at least $50 trillion, which is a huge, huge number. That's basically the GDP of the entire world for 1 year. And so this is enormous. This is a huge, huge economic impact if that really comes to pass. And I thought I'd start by just kind of going through in order what their things are. The biggest impact of AI and robotics is in AI knowledge work. This is using AI machine learning for marketing, for enterprise resource planning, for big data, for smart assistants, sort of revitalizing and changing the nature of business. The Internet of Things is predicted to be worth $15 trillion from now until 2025. It's estimated there'll be 100 billion devices connected to the Internet by 2025, and these are things like sensors, various things. Cars now are really computers on wheels, especially the Tesla. I don't know if you saw, they just got an upgrade where now the Tesla can self-drive. They sort of snuck it in behind the regulators' back. You know, regulators are, oh, should we allow self-driving cars on the road? I don't know. All these Tesla drivers, oh, we got an upgrade, now it can self-drive. So, you know, quite amazing that just happened like a couple weeks ago. Cameras everywhere. I'll talk a little bit about that. Meters, wearables, big thing. Robot manufacturing, estimated to be $10 trillion of value added over the next 10 years. There are now 420 Chinese robot companies. That's mind-boggling. Foxconn, which is the biggest consumer electronics manufacturer, they make the iPhone and the iPad and the Xbox. Pretty much most well-known consumer electronics is built by Foxconn. It's a Taiwanese company that primarily does manufacturing in China. Apple got a lot of flack a few years back because Foxconn working conditions were not so great, and some of their employees were jumping out of the window committing suicide, and Apple got a lot. And so, big, huge thing. At that time, the president of Foxconn said, "All right, forget all these darn employees. I'm going to build 1 million robots and get rid of all the employees." Well, they haven't quite done that, but they're building about 30,000 robots a year. These things called Foxbots. And with the goal of replacing much of the factory work by robots. Similarly, in southern China, in Dongguan, there are now 1,500 companies which are involved in a program called Robot Replace Human, in which they are basically, for all the human factory workers that they can, they're replacing by robots. They just did the first one, and productivity went up, cost went down, you know, huge win, and so they're really rapidly doing that. So robot manufacturing, China is pushing especially fast on that. Healthcare, estimated to be $10 trillion by 2025. This involves everything from just, you know, how do you manage medical records? How do you diagnose disease? We've got all these papers coming out all over the world about health-related, you know, effects of drugs, different metabolic systems. AI systems should be reading all of that and using that to help do better healthcare. Robot surgery is becoming a big deal. especially brain surgery. The robot can be much more precise than a human surgeon can be. And also I just saw a talk on somebody with a robot hair replacement surgery. Apparently in hair replacement, you take little things of hair from the back of the head and you put them on the top of the head. And apparently it's really tedious. It's hours and hours and hours of hundreds of these little things. And human surgeons just get really tired. Whereas with a robot, that's actually a pretty easy thing. The robot just cranks away. So apparently that's become a big deal. Self-driving vehicles, that's probably the one that has been getting the most attention recently. If you live around here, you probably see lots of Google self-driving cars driving around. But the potential impact on society, both on eliminating accidents and in making our transportation system much more efficient, is dramatic. It's estimated that there are currently 10 million jobs doing driving and delivery of some sort. If you look at a map of the United States, many states, the #1 job is truck driving. And potentially all of that is replaceable. I mentioned Tesla's got a self-driving upgrade, Google's got their self-driving car, Apple is supposedly working on a self-driving car. People have been following these unmarked self-driving cars and they go into the Apple parking lot. All the car companies are working on that. There are now self-driving semi-trucks for delivery. On agriculture, like tractors and so on, they've had self-driving tractors for years now because there's less of an issue of running into pedestrians and so on. And then in Australia, there are a lot of mining companies, Rio Tinto and so on, and they have self-driving rigs that do their own, moving around of ore and so on. So huge area. 3D printing, estimated to be $2 trillion by 2025. This kind of thing, little plastic cups, that's probably not a huge market, but there's starting to be 3D printers now that can print multiple colors. There's some that are being able to print metal, some that are able to print circuits. Before long, you'll be able to not just, print continuous materials, but put in like little chips in different places, little displays, and so custom electronics 3D printed. That could potentially be really big. And then on the big scale, China has also been really pushing ahead on 3D printed buildings. And so here's an example of a company called WinSun that printed a 12,000 square foot villa. And so that catches on, and it looks pretty good. I mean, I don't know what the inside looks like, but, and I think they did it in a couple of days, and they've done smaller houses in I think they had one thing where they did 10 houses in one day. And so the US building construction industry is currently $1 trillion a year and employs 5.8 million employees. So this has the potential to really dramatically transform that market. So because of all this excitement and all this activity, and we're seeing, boy, 10 years is not a long time, there's really $50 trillion of value, and that's the low end of their estimates. It's really somewhere between 50 and 100 trillion if you read what they say. That is a very enticing possibility, and so there's been a ton of investment in startup companies in this area. And several $1 billion over the last few years. Here's somebody's list of 633 artificial intelligence companies, little startups doing all kinds of different things. And if you plot how much money is going into these and the number of startups, you can see there are a bunch of different topics here. But the two big ones here, this one and this one, about $1.5 billion and about 250 companies, or more than that, 300 companies, something like that, are in deep learning. So deep learning has suddenly become the hot buzzword. You see deep learning this, deep learning that. So what is it, and why is this happening? And what are all these companies doing this deep learning for, and what is that? Well, so what is it deep learning? So I'll talk a lot more about specific examples, but just to give you a little bit to start with. Yeah?
We will be sharing these slides. There's a lot of information.
Oh, yeah. The slides are available on my website, steveomohundro.com. And they're also on SlideShare. So, and if you want to put it on the meetup, that would be fine too. And you're videotaping it, right? So there'll be a video up there too. So a deep learning neural net is a computational system that is an artificial neural net, and it's got lots of layers, and that's what makes it deep. And I'll say a lot more about why that's interesting and what does that lead to. Here's an example of a system that's supposed to take pictures of somebody's face on the input and predict what their age is. And the way it does that is it takes the face and it runs these neurons, these artificial neurons. It scans over the face, evaluates all these neurons. They have all kinds of weights in here, and it makes a prediction of the age. And it's a learning system, so you have a big database of pictures and the age, And you train this thing. You adjust all the weights so that it does well on the training set, and then you hope it does well on a new person. Actually, Microsoft has a tool live on the web where you can put your picture in there and it'll tell you how old you are. And it's significantly underestimated me, so I don't know if it's I don't know if it's actually trying to be accurate or if it's trying to feed people's vanity. So why deep learning? What's going on here? As I'll say, the whole field of artificial intelligence has had big ups and big downs, and it's swung back and forth. Lots of different approaches, big vicious fights, funding, lots of funding, and then AI winters where there was no funding. Well, this is the hot one, and this one really seems to be doing very well. Just in the past, 5 years or so, we see speech recognition. There was a big test called Timid that everybody compared their systems on. They would try all this stuff, and they eke out a couple percent every time, and whole teams would work on hidden Markov models and all this stuff. Well, in comes deep learning neural net, and it blows them all away. Best performance. And so now all these systems on your phone for recognizing speech, Cortana is what Microsoft has. Skype has a speech recognition translation thing. Google has Google Now. Apple has Siri. Baidu has a recognition thing. Nuance has it. They're all using deep learning. So suddenly, big sea change in the way that you do speech recognition. Image recognition, similarly, there's this big test set called ImageNet. And in 2012, the deep learning systems blew away everything else. Image captioning, same thing in 2014. All kinds of natural language things, trying to understand language, do different things. Sentiment analysis, that is, given a sentence, is this sentence saying something positive or negative? Like think about movie reviews. Somebody says, yeah, this movie's great, or oh, this movie sucks. But it could be more complicated. It could be, you think it's a good thing, like, wow, this movie is so good, I'm gonna give it to my worst enemy. So you have to figure out from that, oh, he said it's so good, but he really means it's terrible. And so there's some subtlety there. These deep learning systems do very well on that. Translation, say from English to French. Semantics, meaning, and that's what we'll talk a lot about here. Drug discovery, figuring out, how do you design a new molecule that does something. Merck has a challenge that was built that the deep learning nets succeeded at in 2012. And then recently, Google paid $500 million for a company called DeepMind. Why did they pay $500 million for a little teeny startup? Well, because this thing played video games really well, and I'll tell you about that. 49 different Atari video games. That was last year, and I'll say more about them in a second. So, okay, great. So that's all this excitement now. Is it real? Is it true? Is this something? There's been a lot of hype around AI. And so I thought I'd give you the context of where did this come from, and so you can get a better sense of what's really real and what's not. So the term artificial intelligence was actually invented in 1955. John McCarthy, this fellow here, this is a picture of some of those original participants when they were older. I think this might be like the 50th anniversary of this or something like that. He put a proposal in 1955 saying we want to do this summer project on artificial intelligence. We want to spend 2 months, we want to have 10 people, and we want to spend $13,000. And what we want to do in this 2 months is we want to figure out how you can use computers to do natural language, neural nets, self-improvement, abstraction, and creativity. Needless to say, I didn't quite finish all of that. Early on, there was a lot of kind of thinking that, oh, this can't be that hard. It'll happen in a couple of years kind of thing. Well, it's taken a lot longer than they thought. John McCarthy ended up in 1963 starting the Stanford AI Lab. Marvin Minsky in 1963 ended up starting the MIT AI Lab, partly based on things that they've been discussing as a result of that original conference. And they kind of polarized the whole field into two approaches that you might think about, which people called, back then, they called it the neats and the scruffies. And the neats had the idea, and John McCarthy is sort of the champion of that really intelligence should be mathematically precise. And that what thinking is thinking is a form of logical inference. It's really a kind of mathematics that's going on. And when you have representations in your intelligent AI system, that those should have a precise semantics. So if you've got some neuron in the middle there or something, it has a value, that value should mean something. So that's sort of the approach that he championed. On the other side, Marvin Minsky and a bunch of other people had the idea that no, that's not the way that brains work. The only intelligence we know of in this world are brains,
And brains don't start knowing anything about logic. Logic is a complicated thing that's hard to learn and so on. That in fact, they're made of adaptive elements, neurons. And these adaptive elements are self-organizing. The brain sort of organizes itself through the developmental process and through learning. Brains sort of figure out the right structure. And so learning is a critical piece, and the semantics should not be built in by somebody with an idea of what things should mean. It should emerge out of this thing. So that was a sort of neat, scruffy thing. In each of these fields, the field has kind of swung from one to the other, and each has gone up and gone down. So just to kind of give you the flow of what happened with the NEAT philosophy, trying to find a mathematically precise structure for what intelligence is, that really started back with Aristotle, 2,500 years ago. He was trying to figure out what are the rules of human thinking, human logic. And so he created logic. Guys like Leibniz in the 1600s had the idea they wanted to make a machine that could manipulate symbols and replace and do what humans did. That got formalized in the late 1800s, Frege, Cantor, and so on. Mathematicians developed mathematical logic, and finally, earlier in the century, a precise mathematical structure for reasoning was developed. Chomsky, Noam Chomsky, the linguist, tried to create a formal structure for language in 1957, and McCarthy brought all that into AI. They had a great time in the 60s, they're cranking away, they thought it was going to be really fast, they did all this stuff, but they didn't really get that far, and in 1973, the physicist Lighthill in Britain wrote this report saying, this stuff is garbage, nothing has come out of this is a waste of money, stop. And so the British said, oh my God, he's right, they cut all funding. And then the US said, oh my God, the British are cutting funding, we're going to cut all funding. So this created what was called the first AI winter in 1974. There was very little funding to do anything on AI. So this was kind of a drag, and some people kind of hunkered down and so on. And then around 1980, people created the idea of expert systems, which were very simple logical kinds of systems. And the Japanese got really into this. They created something called the 5th Generation Project. And they developed special purpose hardware. There's a programming language, Prolog, which is a logic programming language. Bayes nets were created in 1905. Sort of a resurgence, everything was great. And then around 1990, the second AI winter came, where expert systems really didn't work that well. They didn't scale that big. Prolog didn't scale it to large systems at all. The 5th Generation Project in Japan kind of faded away without actually doing anything. US cut funding again, and this created a sort of trauma in researchers' things, sort of the Game of Thrones, brace yourselves, winter is coming. So if you talk to people who've lived through this period, they look at today's thing like, oh, they're hyping deep neural nets and all this, oh my God, watch out, it's gonna get cut, it's gonna get cut. So there's kind of a worry about that. The Scruffies had their own little ups and downs. Probably the first Scruffy system was something called the perceptron by this guy Rosenblatt in 1957. And just to kind of get a sense, so a perceptron is a single neuron that computes a linear set of weights applied to some inputs and thresholds it and says it's a 0 or 1 according to whether that linear combination is positive or negative, and he had an algorithm for adjusting these weights. This so excited people. Here's a quote from the Navy. The embryo of an electronic computer that the Navy expects to be able to walk, talk, see, rate, reproduce itself, and be conscious of its existence. So they got that just from this one little thing back in 1957. Needless to say, that didn't quite pan out as quickly as they maybe thought it would. And in 1969, Minsky and Tappert came out with this book called Perceptrons, in which they showed that these perceptrons were actually not that powerful, and that in particular the XOR function, the exclusive OR of two inputs, could not be computed by a perceptron. And so everybody got all upset, oh my God, we've been duped, this is terrible, it doesn't really do anything, and you got kind of an AI winter in the Scruffy side. Around 1986, people said, well, that may be true for a single perceptron, but if you have multiple layers of perceptrons, they can actually compute a lot more stuff. And so multiple layers are good. The problem was not the perceptron and learnable elements and dynamic computing things. The problem was that you had too simple of a system. And so backpropagation was an algorithm for taking the derivative of a multi-layer system with respect to the weights so that you could learn a multi-layer system. During this era, most of the neural nets had 3 layers. There was a hidden layer which kind of captured the interesting things. And people used this for lots and lots of different tasks. A good friend of mine made a backgammon playing program using this that worked really well. It was used for speech recognition, classification, all kinds of stuff. So that was very exciting. And then in the 90s, along with the other AI winter, there was kind of a neural net winter also here, and they kind of hunkered down and so on. Until 2007, the word deep learning came where, oh yes, these little neural nets are only 3 layers. That's not enough to do anything interesting. We really need 10 layers, 20 layers, maybe 100 layers. And we now have, and they invented some good algorithms for training those, and that started beating all the contests and so on. And so that's where the recent excitement is coming from. So let's think about how natural language should work. Let me start with what the neat vision is. If you're in computer science, you know how a compilation works, like a C compiler, which is supposed to take source code at its input and produce machine code at its output. And the way it works is it goes through a sequence of steps. You start with the source code, you do lexical analysis, you figure out the tokens in the programming language, you then parse those tokens through a parse tree, you then take those parse trees, you do semantic analysis, you create some kind of internal intermediate representation, then you use that to do code generation, you create a new form, and then you do code optimization. So each of these stages has precise mathematical meaning, we know exactly what it is, and we can just go from here to here to here, bing, 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 bing. So it's a nice image, that's sort of the neat fantasy of how intelligence works, and it works beautifully for compilers, programming language compilers. So let's say you wanted to do natural language, human language translation. What would be your analog of that? Well, first you take, say, some written text, you break it up into words, that's tokenization. You stem the words, which is you get rid of any inflections. You then do tagging, like what part of speech are these different things. Based on the tags in the words, you do parsing, you try and create parse trees. From that parse tree of the sentence, you create a logical representation. Somehow, what does this sentence mean? And then from that logical representation, you can create its translation. And this was sort of the structure of all the natural language systems from that earlier era, but they didn't work that well. And worse than that, it also fit very naturally into the way the linguists were thinking about this. So in particular, Noam Chomsky, he had the idea that the syntax of natural language is something which is totally separable from the semantics, the meaning of it. And that you should be able to write a grammar for English, and he did mathematical work on the natures of grammars. If you study computer science, you probably learned about regular grammars and context-free grammars and context-sensitive grammars. That was Chomsky's innovation in 1957. And he thought this is the way that language should work. So and that, to some degree, you can have success with that. Here's this book that's a comprehensive grammar of the English language, in which they try and suss out all the rules of syntax. The book is 1,792 pages long. So unbelievably complicated. And poor linguists flail away. A person's whole career might be on one paragraph in this book. Once you've got the parse tree, once you've got the syntax, well, now you got to understand what the thing means. So where does meaning, how does that semantics come? So they fussed around with all kinds of different things. Frege, who's one of the sources of mathematical logic, was really motivated by the meaning of natural language. Finally, in 1970, this guy named Montague, who unfortunately was murdered, but before he was murdered, he wrote this paper, which is called English is a Formal Language, which is to actually treat the words in language as if they have a precise meaning. And he recognized that there's something called typed lambda calculus, which if you're a computer scientist, that's a pretty familiar thing. Back then, nobody knew about it. And so he realized that was a really natural way to map natural languages into this thing, and it's now become known as Montague Semantics. And the linguists mostly built on top of that idea. And so that was the model of how natural language thinking works. Linguistic rules are complicated. In English, the phrase, a velvet new comfortable dress, is not right. That doesn't sound right. If you're a native speaker, you go, what? That's not quite right. But it's hard to say why it's not right. Whereas if you say a comfortable new velvet dress, that's okay. So one of the questions, what's the difference between these two things? So just as an example of a linguist rule, is they say, oh, well, adjectives, modifiers of nouns, come in 8 different flavors. Which are like the opinion, an opinion adjective, a size, a shape, an age, a color, a national origin, a material, a purpose. And if you've got more than one adjective, they have to come in this order, otherwise it's not good English. That's really bizarre. And not everybody agrees on what this order should be, and there are exceptions. So, kind of weird. And so English, which is especially bad, I think, is full of this kind of stuff. So what do you do about that? Well, in 2006, a bunch of people, this is just one of many papers that did this, took the simplest statistical model of what language might be, something called an n-gram. So a bigram is just pairs of words that appear in documents, and you just accumulate. Well, how often does the dog appear? Yeah, the dog is there a lot. How long does dog the appear? Not very often. And so you can keep track of all pairs of words, how often do they appear in a big corpus of data. And then instead of bigrams, you do trigrams, 3 sentences. The dog ate. Okay, that's a good combo. And work all the way up to, say, 5 grams. And if you've got a big corpus with 5 grams, that gives you a kind of a statistical model of your language. And you can take translated documents, like they often used to use legal documents, which in Canada, legal documents have to be both in English and in French. So you have both the English version and the French version. And you can look at the correspondences and then use that in a very simple statistical model to do translation. And the shocking, surprising thing that a lot of these people discovered was that these simple n-gram models of translation did a better job than the human linguist, huge 1,700-page complicated models built by hand. So that was shocking. Yeah?
What was it, the Rosetta Stone that had translations of Greek, Egypt, and all that? Has there been any studies to compare that to a computer-generated translation?
That's actually a really interesting question. Yeah, the Rosetta Stone is this thing where they found a language that we knew, and I don't remember what they are, and some languages we didn't know. I think cuneiform was on there, and so they used that as a way to figure out, well, what does cuneiform mean? The trouble is, it's a pretty small sample set. These techniques work best when you have lots of data. In fact, any machine learning thing, the more data you've got, the better. And the if you only have a little bit of data, then the linguists are great. The linguists can really add a lot of value. If you've got a lot of data, then the cost of the linguist is not worth it. And so in 2009, Peter Norvig and some other people wrote this nice little paper saying that, gee whiz, data is cheap, especially on the internet, and it's getting cheaper and more plentiful. Every day, people probably write more than all of recorded history previous to this, that kind of thing, So we have tons and tons of data out there, and our computers are getting super fast. So we can process all that data, and much, much cheaper than hiring a linguist to try and figure out what's going on, or hiring human programmers to try and build a complicated model. So this sort of marked a sea change from complicated human-built models to automatically built, very, very simple models, but with a lot of data serving as training. In 1962, another little hint that the nature of language may be a little different than the way Chomsky and those guys were thinking about it. 1962, the psychologist Roger Shepard did some really interesting work in which he interviewed people psychologically about, did they think purple was closer to blue or was it closer to yellow? You should get a sense of how close different concepts are in people's minds. And he had an algorithm for embedding concepts in a geometric space, and he discovered that the colors very naturally almost lie in a perfect circle. You do the same thing with tones. You discover that the tones, pitches, lie on almost a perfect helix, in which tones which are an octave apart are very close, but things which are 3 semitones apart are very far away from one another. And he discovered that if you ask people, you show them this picture and you say, is this a rotated version of that they can do that task, but the more rotated it is, the longer it takes them. Basically, the time it takes them is proportional to how rotated it is, which suggests that whatever representation we're using, the geometry of the world is somehow encoded in. And then they did this for words in language, and they discovered that, yes, we have a notion of when 2 words are similar, and they apparently form a geometry. And so one of the really exciting things that's happening with these deep learning systems is that the deep learning network is discovering this kind of geometry. And the old idea was that, things which are similar to one another should be represented near one another in some abstract space. So we're going to represent words by vectors, by just a bunch of real numbers that encode a point in some abstract space, and close vectors should represent similar contexts. This comes out of an approach to semantics, which is becoming more and more interesting now, called distributional semantics, which says that what a word is, what the meaning of a word is, it used to be like, a word is like what it denotes in the world. In distributional semantics, the meaning of a word is the statistics of the words that can appear near it. So this is a real shift in how you think about what words might mean, and the two words are similar if they can appear in similar contexts. If the words that are around them tend to be the same. And it's a very strange way of thinking, and we'll see it leads to a lot of interesting things. So here's the deep, or it's not very deep, just 3 layers, neural net, where you have a word in a document, some text document, and you train it to try and predict the words on either side of it. And then this little representation in the middle is the vector representation. So this is something called Word2Vec. You can get it open source on the web, and it has amazing properties. And so people have been discovering all these weird things. So in addition to this property that words which are kind of like one another tend to be represented by nearby vectors, they discovered there's a kind of algebra of these vectors. Vectors can be added to one another. And if you take the vector for king, and you subtract the vector for man, and you add the vector for woman, it turns out to be queen. So this is kind of weird. King minus man plus woman is queen. And people started exploring this. So this is sort of somehow capturing gender, the relationship of male to female gender, as a translation in this vector space. They discovered that tense, like past, present, future, temperature, location, plurals, all of those are represented semantically by translations in this vector space. And so here's a little diagram. The vector space is big, say hundreds of dimensions, maybe 200 dimensions. But you can project it down onto 2 dimensions to capture some of the variation. And this shows a little bit more of the vector which goes from princess to prince, or from prince to princess, from king to queen, from hero to heroine, from actor to actress, and so on. Why is it that all of these should be represented by the same vector? If you think about it, where these words get placed in this space is dependent on the context in which they appear in your corpus of data. And so you might see the sentence, the man ate his lunch, the king ate his lunch. But then you might see the woman ate her lunch, the queen ate her lunch. And so the context, the blank ate his or her lunch, those 2 contexts sort of capture whether whatever this word is going to be masculine or feminine. And so that's where this vector emerges. So it's one way of understanding that. So people have been playing with this. You can just put in anything and see what happens. You discover that Paris minus France plus Italy equals Rome. Kind of makes sense. Human minus animal equals ethics. That's a little bit weird. Obama minus USA plus Russia equals Putin. Makes sense. A library minus books equals hall. That's a little bit strange. Biggest minus big plus small equals smallest. Ethical minus possibly plus impossibly equals unethical. Picasso minus Einstein plus scientist equals painter. Forearm minus leg plus knee equals elbow. Architect minus building plus software equals programmer. So we have a kind of semantics emerging in the algebra of this representation. Yeah?
Is it something existing, or you're kind of giving the semantics?
It emerges. Nobody put it in by hand. You can go to a WordNet and or Word2Vec and try it out. And this is stuff that people have discovered in the structure. Yeah?
The semantics can be dependent on the multiple contexts, like for example, some words can appear in multiple layers of context. So which one is good?
Yeah, so in this one, I think they're taking like 2 words on the left and 2 words on the right, but you can play with that, right? You can do 5 words on the left, 5 words on the right, and we'll see there are more sophisticated things that don't have a fixed window. I mean, a fixed window is kind of artificial in the middle there. But so lots and lots. So one of the things I'll say about deep learning nets, there are a few basic principles, and then you can put them together in thousands of ways. And so it's kind of like a Cambrian explosion, like in biology. There was this moment when somehow biology, used to be these boring little creatures, and at some point they discovered some new thing, and this flourishing of, millions of new species showed up, exploring all kinds of weird stuff. Sort of feels like we're in that zone now with these neural nets, that you can take this basic idea and play with it in a million ways and maybe discover something really cool. So let me give you, so that was language, and we'll say more about language in a second. Let me give you the corresponding thing for vision. So vision is the task of you look at something and you say, oh, that's a chair, oh, that's a shoe. Very easy for us to do. It's been the bane of AI since its beginning. Early on, they thought vision would be easy because it's pretty easy for us. And so they assigned this one guy, Roberts, for his master's thesis over a summer was to solve the vision problem. And what's amazing is he actually figured out a whole bunch of stuff and did a pretty good job. But until recently, vision systems have really not worked very well. And the probably most influential guy in vision was this guy, David Marr. And he had a kind of neat perspective on the way you do vision. In comes an input image. You get the perceived intensities, how bright is each pixel. From that, you create what he called the primal sketch, which is you do edge detection. You figure out like where the edges in the picture are, and you link those edges up into curves. You find the ends of the curves. You basically label all the parts of the picture image in that way. You then go from that stuff and you form what he called the 2.5D sketch, which is each little patch of the image. You try and figure out like what angle, what surface it is, where the surfaces end. You sort of make a two-dimensional picture that has some 3D information. And then you form a 3D model out of that. You piece it together, you say, oh, this is a cylinder, and oh, a chair has a cylinder here for this leg, and another cylinder there, and a flat thing for the back. You build a 3D model, and then somehow you have a database, a knowledge base of 3D models, and you try and match your 3D model with what's in the knowledge base. Oh, it's a chair. That's the kind of thing. Kind of worked, they did a few different things, like for polyhedra, they could kind of get it to work, but for real world systems like that chair, who actually input the chair? Oh, is a chair something which has a seat in the back? Well, but what about the angled thing here, and what about that, and what about a sofa, and what about a stool, and complicated. And so they would hand build these things, and they just didn't work very well. Deep neural nets have been really killing it on vision. There are now systems that you can play with live on the web. You can put pictures in, and it will put labels on that picture. Oh, it's a little girl eating pizza with her father. That kind of thing. How is it doing that? Here's an example of a nice system that does face recognition. So you've got an image of somebody's face. You want to figure out who they are. Trouble is, maybe their head is tilted like this. Maybe their head is turned this way. Maybe there's weird lighting in the room. Maybe they just shaved. Maybe they had a bad night last night. So all kinds of variation, and you'd like to say, oh, that's Bill. How do you do that? And so there's this database called Labeled Faces in the Wild, LFW. It's a big, big database of just ordinary faces gotten off of probably Facebook and labeled by who they are, with I think about 10 versions of each person. And there's a contest. Oh, can you make a learning system which tries to recognize who this is, and then there's a test set to compare against. And lots of different systems are trying it. And in June, Google released something called FaceNet, and they showed it had 99.63% accuracy on this set, which cut the previous best error rate by 30%. It's a huge, huge improvement. It's a 22-layer feed-forward network with 140 million weights. Requires about 1.6 gigaflops per image to do the processing, but if you've got fast hardware, a lot of these systems now run on graphics hardware, so it's not too bad. And it uses convolutional nets, pooling nets, and normalization nets, and works really, really well. So this is kind of cool. Well, that's Google using all their resources and their huge compute power and all this kind of stuff. Well, last week, CMU said, well, we really like this FaceNet thing, but we don't like the fact that it's proprietary. We're going to make a copy of it, and they invented something they call OpenFace, and they just released it. All the source code is freely available. It's not quite as good as FaceNet because they don't have as big a training set or as big computers, but they're getting 84.83% accuracy, and they have less than a tenth of the training set of Google. So presumably, if they up their training size, they would do better. Did I see a question? No. Interestingly, so face recognition, that's one of those things where we're starting to get into territory where is this a good thing or is this a bad thing? I knew people when I used to do some machine vision things, and I knew people who said, I will not work on face recognition because bad people will use it for bad purposes or something like that. And it's an issue. And so AI in general has this issue of it's got huge positive uses and maybe not so positive uses. And so on their website they say, please use responsibly. We do not support the use of this project in applications that violate privacy and security. We are using this to help cognitively impaired users to sense and understand the world around them. So maybe. Yeah?
Could this software be used for objects, not just faces?
This is pretty much tuned to faces because their pipeline is, they have an input image. First you have to detect the face, to find the face in the image. You then have to sort of normalize it, rotate it, scale it so the pretty much they usually use the eyes, makes the eyes at a fixed place. And then once they've got that, they crop it, and so that's the thing they actually do the recognition on, that cropped face. They then run the deep neural network over it, convolutional, it's got lots and lots of copies of little nets, creates a representation, and then they can look it up in a database and recognize it. So some of this is kind of tuned specifically to faces, but this part is very, very general. And so right now, the state of the art is any class of objects you might be interested in, you probably want to tune your network for that. Before long, you'll have general things that can recognize anything. So just a kind of little social commentary here. Cameras are getting really, really cheap. Every cell phone has at least one camera, and most of them have two now. And if you go to Alibaba, which is a big Chinese marketplace, you can look up cell phone camera modules, and you can find them for $3. And on eBay, there's also one that's for $3. So $3 cameras. So I expect we'll have cameras everywhere. For surveillance, for all kinds of stuff. Face recognition now, open source, pretty good version. There's also body recognition. So recognizing, here's a thing of people are recognizing people from their walk. So even if you're wearing a mask, you're a robber, bank robber, you got a mask on, how you walk to some degree identifies you. And Facebook has a thing which can recognize you if your face is turned the other way. Somehow it looks at your shoulder. I don't know exactly how that one works. So we got cheap cameras and face recognition and body recognition. We're moving into an era in which we should expect every person on the planet basically to be tracked in some big database. And you can kind of push against that and say, no, I want my privacy, that's not going to work. Probably not going to happen. There's a really nice book called The Transparent Society by David Brin, which says, yeah, privacy was a nice thing, but in fact, having total transparency and openness is probably pretty good too. And so you can look at that and see what you think about it. But I think this technology shows that's one place that we're going very rapidly. So all this is great. So far I've talked about feed-forward networks. So these are neural nets that take some kind of an input, they do something, a few stages, deep net, maybe 10 stages, maybe 100 stages, and then they produce something. That's great. But if you look at biological networks, and there are three kind of core networks in the human body. We've got our genes. We have DNA in every one of our cells. DNA codes for proteins, and those proteins affect the way that transcription happens. So there's a graph of this is all the genes on one of our chromosomes, chromosome 22, and this is like which ones affect which other ones. It's a kind of computation. It's a intelligent computation that makes our bodies work. Similarly, the human metabolome is proteins affect and chemicals in the cell form a graph of what things they turn into. Big, complicated network like this. Biologists look at something like that and they go, oh my God, it's so complicated, because they spend their whole career on that one, something like that. Computer scientists looks at that and go, oh, is that all? Microsoft Word is over 1 million lines of code. That's nothing. So biology is very rapidly coming into the computational view of things. And then finally, the brain, human brains have a lot of neurons, but they're connected, they form little regions, and those regions have bundles of fibers that connect one together. And they're not that complicated. Here's a sort of graph of the different regions of the brain, something called the brain connectome. And so these three give you a sense of, in biology, what do these graphs of the flow of information look like? They're deep, but they're not that deep. And one of the things that's really important is that they are recurrent. So they don't just go from an input to the output. In fact, in the brain, the initial vision was, you get light in your eyes, the eyes go down the optic nerve, it goes to your V1, the visual cortex in the back, that does edge detection, it goes to higher orders, and it's a big flow. Well, it turns out there are 10 times as many fibers going backwards in the brain as there are going forwards. And so the whole thing forms a very complex recurrent network with cycles in it. And so one of the threads in the deep learning world is that these recurrent nets are actually very important. And if you're interested in this, it's a little hard to wrap your head around if you're just learning about it for the first time. It's a wonderful little blog by Andrej Karpathy, and the links are on here. Say again?
It's called Andrej.
Andrej. Can you say the full name?
Yes, Andrej Karpathy.
Andrej Karpathy. Great blog with all kinds of intuitive stuff. He has a really nice article called The Unreasonable Effectiveness of Recurrent Neural Nets. And he goes through a bunch of examples and experiments and gives you all the source code so you can play with it.
And just to give a few examples, so a recurrent net is one which it has an input, it's got some neural net, and it's got some internal state. And so the neural net evaluates the internal state and the input, and it produces an output, and it updates its internal state. So that's where the loop is. It's got an internal loop. And depending on how you do it, so to understand it and to train it, you unroll the network. So here's an example of a feed-forward network. Got your input in red, you've got the neural net that does something in green, and then its output in blue here. And it just goes from here to here to here. If a typical situation for this would be image classification. I give you an image on the input, and I want you to tell me is it a dog or a cat on the output. An example of a one-to-many would be image captioning, where I give it one image, but maybe an image that will say dog, maybe another image that will say a dog and its puppy. You know, it might have two things. And so you might want a sentence coming out on the output, and the sentence might have a variable number of words, whereas the input still only has one thing. And the trick here is that all of these green blocks are the same network. It's just the same network unrolled in time. And so you can think of time as running from left to right here. And so the image is presented here, and the first time we send it through, it produces the first output, and it produces an internal state, which then it's run again, and it produces another output, and then it's run again, and it produces another output. So we're taking the same network, and we're unrolling it in time. And when we do training, we give it an input example and a desired output. That desired output then affects the weights in all, we do back propagation in time through this thing, but all these three things, their weights have to change together because it's the same network. Another example would be a many-to-one network. An example might be the sentiment analysis, where I give it a sentence input, who knows how many words it's going to have, and it's supposed to say this is either positive or negative. Yes, I think this stock is going up in the stock market. No, this company really sucks. Next one would be many-to-many. An example might be an English to French translation, where you give it an English sentence here, it cranks away, and it produces a French sentence here. And then finally, many-to-many, where you want it to happen in real time. Say you might be doing classification of frames in a video, and you'd like the classification to be coming out frame by frame, so that as the input's coming and the output's coming. So he does a bunch of examples, and most of the ones he plays with are text examples, where he trains the network, the recurrent network, to, based on the previous text in a document, predict the next character. So he does it character by character. He doesn't even break things into words. He says, I'm not going to tell it what a word is. I'm not going to tell that space is anything important. I'm not going to tell it, certainly not going to give it any grammar. I'm not going to tell it what a period is. I'm not going to tell it capital letters or anything. I want it to learn all of that. So he just has this simple network that's got a three-layer recurrent network, something called an LSTM. It's a particular kind of structure, about 10 million parameters, and then a lot of data. And he trains it on Shakespeare, and then once you built it, you can then use it to generate text. It generates a character, and then you feed that character in as its input, and you say, well, predict what the next character is going to be. Then you feed that back in, you say, predict what the next one's going to be. And so you can see what it thinks is good text. So he trains it on Shakespeare. It's producing pretty good Shakespeare. He trains it on all kinds of things. He gives it LaTeX input, and it produces kind of LaTeX documents with formatting and stuff. The one that kind of blew my mind the most is he trains it on 464 megabytes of C code. I think it's the Linux source or something like that. And then he has it hallucinate, create some C code for me. This is its hallucination. It's figured out what comments look like, and it even formatted its comment pretty nicely. It knows to define a function. It gives the function a nice name. It knows to match left braces with right braces. Figures out that parentheses get matched, even separately from the braces. It puts comments in there. It invents variable names. It knows what a string is, and it makes up some weird kind of thing to be the string. So the thing is just remarkable. And yeah.
Does it discover the syntax perfectly, or so in other words, is this compilable?
That's the question, is how much does it really know? It's doing something that looks pretty good. I actually don't know if you could run it through the compiler.
You can write scientific paper.
You could probably write a scientific paper this way, exactly. Yeah. Somebody you can't write.
I don't think this can be go through the compiler.
So it doesn't, I don't think it knows much about semantics of C code, but it's getting the formal, it's getting the syntax pretty good. And the thing that shocked me when I first saw this is if you're a computer scientist, this is a regular grammar. It's a finite state machine. It's just got a finite amount of state. It literally cannot, mathematically cannot represent matched parentheses properly. Because matching parentheses is a context-free grammar. Can't do that. And some of the stuff actually looks context-sensitive, which is even harder. So it's like, how on earth is this thing able to do as well as it is? Yeah?
What is it intended to do?
This is but just a demonstration. And so this is sort of, we'll get to applications in a second, but this sort of gives you the sense of the remarkable, unexpected power. He just cranked out this little thing, wrote a little program. I think the total program is maybe, a couple hundred lines of code. There are open source Python libraries to do a lot of this stuff. Gave it this random, training set he pulled off the web. It's a fair amount of computation. He runs it. Some of these you can run on your graphics card. Some you run all night. And out it's creating something that no human, it wasn't thought that this was even possible 10 years ago. I was totally shocked that you can write a program that can hallucinate pretty good C code. It's just amazing.
Can even hallucinate? Yeah, I think it's different than between a hallucination and something meaningful, right? Like to his point, right? So if this is supposed to let's say infer the syntax from that corpus, right?
Yeah.
I would say that would be a pretty powerful conclusion, right? But if it just generates some random C, which looks impressive, but what does it do?
Yeah, this is not an application. This is a tool to help see what it's doing. These are the applications, right? So you would use it to do all this kind of stuff. Like you could train it to, look for syntax errors in C code, that kind of thing. And so, this thing is more just to get a sense of how can it be doing this. It seems totally magical to anybody who's been working in this area for a while.
The comments almost make sense.
Oh, do they? Anyhow, you should look at his the webpage. He's got a bunch more examples, and they're really mind-boggling. It stretches your brain to see what kinds of models these things are building. And just thinking about the issue of context, we have these supposedly complicated rules of grammar for English. But think of the following sentence. If I say, the rat escaped, everybody understands that. If I say, the rat the cat attacked escaped, that's a little harder to get, but you probably get it, right? Especially if English is your native language. But if I say, the rat, the cat, the dog chased, attacked, escaped, that's perfectly grammatical, and yet it is at the edge of my understanding. I can barely get it. Like, I have to look at it again and so on. So if you think about how we deal with language, we've got something like formal rules, but we're very limited in how deeply nested we can do things. And so I think that's just an example that our syntactic abilities are quite limited as well. So the one that's been generating all this interest is this company called DeepMind, which Google purchased. They're based in Britain. And they published a Nature article explaining their system that plays 49 Atari 2600 games. These are these games, little video games on a simple monitor, older games. The thing that's shocking from an AI perspective is the very same network, without tuning it at all, plays all 49 games. So they have one system which can do all 49 of these, which is showing a certain kind of powerful generalization. It does it by the raw pixels. It gets the raw image from the screen, just what a person would see in playing this game. And it beats all previous AI systems for playing these games. And it does it in interesting ways. There's a video you can watch that shows how the thing plays. And it's discovered, like there's this breakout game where you're supposed to shoot little blocks down or something. It figures out a way to break out the blocks on the left to get the ball to bounce around up on top in a way that no human had ever done before, and all kinds of weird stuff like that. It beats humans on about half of them, so the very best human players are still better on about half the games, but they seem to be still improving it. In May, they said that they're now up to 100 games, and so they haven't, I don't think they've published that one yet. And then there's a video of the Royal Society in which the president of this company talked about where they're taking this same network to 3D games, like flight simulators and racing games. And so there's an open source racing game called Torx. It has a little car on a road, and you drive this little car around. And just anecdotally, I don't think they published anything on it yet, the system learns by, and you don't tell it anything about it. You don't tell it what a car is, you don't tell it anything except you have a signal saying, like if you crash, that's bad. When the game sort of crashes, it's bad, and if you get a reward, then that's good. And then they let the thing run all night and see what happens. They came back in the morning, and it suddenly is driving this car, it's doing maneuvers, it's passing other cars, it knows about banking on the curves, it's discovered all kinds of stuff. So that's pretty amazing and shocking. I'm sure they did some experimenting, but not a huge programming effort as it normally would be. And I believe that one you could directly apply to, say, for example, creating an autonomous drone. So right now, drones are becoming a very important industry. They're also starting to cause a lot of problems. There are, I think, 100 near misses of jet airliners and drones in the last few months. But it's estimated to be a $98 billion business from now till 2025 for delivery. Amazon's into it, Google's into it, surveillance, good and bad, agriculture, military's using a lot of drones, and police forces are using drones. Today, there's always a person controlling these things. I think that kind of net could easily, in a particular environment, like agriculture loves drones because right now they have to overuse herbicides because if one part of their field starts getting some kind of fungus or something, that could destroy their whole field, and so they basically blanket it with products. Whereas if they have a drone that can inspect the field every day, they can tell when something bad has happened. And so having autonomous drones could be potentially very valuable. So great, sounds like deep learning is amazing. Yeah, let's invest $1 billion in startups. Yeah.
If you go back to previous the deep Q, what does deep Q stand for?
So there's something called Q learning, which is, and this is in the school of what are called reinforcement learning systems. So the ones I was telling you about before, you are what are called supervised learning, where you have inputs like a face and what the age of that face is. And then the system is supposed to learn that pairing. When you see this face, produce this output. Reinforcement learning systems don't work that way. They work by the system does something, and then you say, good system, like a dog, like you might train a dog. You don't tell the dog, okay, this is how you shake your hand. You say, good dog or bad dog, right? And so reinforcement learning just gets a signal, good or bad, and it has to discover itself what it did that made it good. And the thing that's challenging is the thing that it did that made it good may have happened, a few seconds before or a few minutes before. And so reinforcement learning systems, in particular these DQ systems, are able to do credit assignment through time. And they can discover that, like in this case, if the car crashes, it may be because I just turned the wheel into the wall, and that was bad. That's pretty easy to learn. But it may be that, 5 seconds earlier, I should have been going on the left lane, and instead I went in the right lane. And so how do you figure out that it should go there? And so Q learning is one approach to that. And the deep neural net is, they're taking a standard algorithm. Q learning is an old algorithm, but they're using deep neural nets to try and discover the structure of that algorithm. So deep learning sounds great. Yeah, let's invest $1 billion in startups. Woohoo! We're going to revolutionize everything. Well, there are a number of issues, a number of problems. Several papers have come out saying, I don't know about these deep learning nets. Here's one that has discovered that, like something which is supposed to recognize cats and dogs, that there are other weird inputs you can give that it very confidently says, yeah, that's a cat. Yeah, I think so. And so, particularly testing these systems on areas which they weren't trained on, they don't necessarily do very well. So they have blind spots in the middle. And this is a problem from a business point of view because typically a business has a problem they want to solve. I want to make a self-driving car, and it should do this. I want to detect credit fraud based on these variables. They don't really have reinforcement signals, so it's not very effective. We want confidence that the system's actually going to solve that problem. If a human programmer, develops an algorithm for detecting when there's credit card fraud, then that programmer knows that they did it according to a certain model, and you can be pretty sure if they're competent that they did it right. With this system, we just let it run overnight. We don't know what it did. You get it, it's got 1.5 million weights. What the heck do they mean? There's no semantics necessarily anywhere. And so, how do you get confidence, first of all, that the thing solves the problem? More important, especially as these systems become more integrated into society, how can you be sure that they don't do things they're not supposed to? How can you be sure there's no unintended consequences? Similarly, as AI systems and autonomous systems become more integrated into society, we're going to have legal constraints on them. And very soon, if not now, we're going to have autonomous cars driving in the road. They're supposed to follow the rules of the road, right? They shouldn't speed. They shouldn't bump into pedestrians. They should do good things. How can we be sure that this autonomous system does what it's supposed to? Corporation, they may have corporate rules that we want to follow. We may have design constraints, like, oh, I want to have a safety factor of this amount. None of those are very easy to do with neural nets of this form. So stepping back a little bit, so in the deep neural nets, I mostly talked about architecture. I talked about what the structure of the system is. I haven't really said much about, well, what should it be? What should it be doing? And what is the nature of intelligence? That's the sort of core question of AI. Well, it turns out that way back in the 1940s, John von Neumann created the foundations of microeconomics and game theory. And as a part of that, they identified what is now known as rational decision making, which is, let's say you have a precise goal of something you want to happen in the world. How do you best make that happen? How do you do it? And his algorithm is actually very simple. It's first you have to encode what you want in something the economists call a utility function. This is just something which is larger when it does what you want and it's smaller when it's what you don't want. You have some kind of a model of the world. You consider all the possible actions you might take right now, and you estimate, based on your model, what's your expected utility. You take the action that has the highest expected utility, the one that's most likely to produce what you care about. You take that action and you see what happens in the world, and it may be that your model of the world wasn't quite right, so you may have to update your model, and there's something called Bayesian statistics that you use to do that update. So that's the algorithm. In some sense, this is the algorithm for intelligence. And we can make it precise. You've got an intelligent actor in an environment. The environment is giving the actor a sequence of sensations. The actor, the intelligent agent, is taking a series of actions. He has a utility function on sensation sequences, which says how much I like this. I like this set of things that came. And he has a probability distribution on what sensations are likely to come if he takes a certain set of actions. And then this is the definition of rational action. You just maximize the expected utility of, you take the action which gives us the highest likelihood of what you want to happen. This is the formula for intelligence. So in some sense, this is it. We could just replace all this AI stuff just by this formula. Except, unfortunately, say again?
It's a greedy offering.
It's greedy in the case in which things are are deterministic. It's greedy. Basically, do what's best. In the case where there's uncertainty, it's a little tricky because you have to balance. If I do this, I got this chance, and if I do that, I got that chance. How do we weigh those? It includes within it Bayesian inference, search, and deliberation. So why doesn't everybody just do this? Well, unfortunately, it's really, really expensive. That's the number of computational steps, and for most realistic problems, it's just too much. So the way I like to think about the goal and the purpose of AI is basically doing this or approximating this, but using as little computational resources as you can. And so you can analyze, as I limit the computational resources, what kind of intelligent solution do we get? You've got almost no computational resources. All I can do is just take the super greedy, which is I always do the same thing, and I just do the same thing that will, on average, do the best. If you've got a little bit more resources, you can do stimulus response. You can sense what's going on, and then just in a lookup table way, based on what you sense, take an action. A lot of creatures do this. This is sort of like how viruses work. They float around, when they get the right sense, they do their thing, and that's it. A little bit more, and you get simple learning. You've got some parameters that you can tune based on your experience. Maybe the world has some uncertainty about how it might be. If you can adjust your performance, adjust the entries in your stimulus response table, you can do better. You see little one-cell creatures that do some of that. Something called epigenetics. If you got a little more room, you can do episodic memory, which is you can actually remember your experiences. Oh yeah, a week ago I went and I talked to that guy and he really was annoying. I'm not going to go talk to him anymore. And so higher animals do that a lot. A little bit more, you can do deliberation. You can reason about. You have some kind of a model of the world, and you say, if I want to get on the other side of that fence, I really should go over to. Should I go to the left or to the right? Well, and you can make those trade-offs, and you can simulate in your mind the possibilities and pick the best one. So some animals do that. Monkeys certainly do it. Dogs kind of do it. We do that in spades. A little bit more intelligence, you do meta reasoning, which is you do reasoning about your own thinking. You say, gosh, if I only knew a little bit more linear algebra, I'd be able to do this neural net stuff. I better go read a book about linear algebra. Something like that. Have a little bit more, you become self-improving. You can actually model your own operation and redesign the structure of your own software. Humans can't quite do that, but we've got a big self-improvement industry that tries to do that. And then finally, if you have enough computational power, you can be fully rational, which is you just totally optimize that thing. So in some sense, you can think of all of these deep learning networks as incorporating certain of these elements in a way that tries to use their resources effectively so that you put your computational power where it actually does some good for you. So out of all this, we're beginning to build systems which can actually model aspects of the world, create semantics about understanding what's going on in the world, understand what language means, understand what images mean, and take better and smarter decisions. This is probably going to transform every aspect of human society. Analyzing camera data, sensor data. IBM just bought the Weather Channel yesterday, and they want to use their big AI system, Watson, to do better weather prediction. Better weather sensors all around. Potentially huge input. Better search, question answering, info. This is one reason Google is so interested. Google just announced that as a part of the Google search engine, they're going to start using a deep learning net as one of the inputs, and it's improving over a lot of their other factors. Analysis and optimization of business processes. Huge, huge industry. Every company has inefficiencies that anybody who works in a company knows about, and so the more you can model what's going on and figure out what really matters and what doesn't, the better. Health monitoring, medical diagnosis, financial markets trading, stabilization. We've had huge market crashes, totally unexpected, weird behaviors. We need smarter systems monitoring what's actually going on. Autonomous cars, trucks, boats, subs, planes. Military is very interested in all of these. Pollution monitoring and cleanup, improved robotic manufacturing, software and hardware design. Eventually, they're estimating that in the next 10 years, 30% of all jobs will be automated. So this is potentially really good, and that it's more efficient and so on, but potentially like, whoa, what is everybody going to do? So big discussions going on right now. What is the nature of society when most people can't do anything that AI systems can't do better? And the initial idea was, it's assembly line workers, they're in trouble, because man, Foxconn is getting all these robots, don't be an assembly line worker, be a white collar worker. Well, this is like, this is white collar work, So software and hardware, you say, no, I'm an engineer, I'm a software engineer, my job is safe. Sorry. Very soon, I believe, we'll start seeing systems being designed in this way that are probably more effectively than people. So exactly what is the role of humans and how do we integrate ourselves with these is a really interesting and big question. So there are a bunch of different approaches to semantics. I've talked about some of them. Meaning, you have to say what the representation of meaning is. You have to say how you encode it. You have to say how did you learn it? Like little kids, young kids, 7 or 8, they learn 10 to 15 words a day. How on earth can they do that? That's pretty remarkable. Communicating, taking the models that they've built and communicating to somebody else, and then reasoning, making inferences based on what they've done. So there are a bunch of different approaches to semantics. I mentioned Montague Semantics for language, which is a sort of formal way. Denotational semantics is big in computer science, representing programs by mathematical things called domains. Mathematics uses mappings into set theory. A kind of newer branch there is category theory. This distributional semantics represents the meaning of words and other things in terms of the statistics of the context in which they appear. The deep learning stuff is all like down in this area. I believe we need to really combine them all. And so my company is called Possibility Research, and we're working on sort of combining all the different levels of semantics. And hopefully, maybe in a year or so, I can talk more about that. That's what I wanted to say. Any questions, comments?
I don't know if you can comment on that, but back to the previous slide, I think these things are almost like orthogonal, I think very difficult to map lambda calculus on I mean, even though, for example, it's related to category theory, but statistics of context and stuff like that, I think they're like not really.
Today they're totally separate.
Yeah,
And the
so-
people that do them, they are in their own worlds.
Right.
And they mostly don't even talk to one another. It was hard to get well, certainly the linguists barely talk to the mathematicians barely talk to the computer scientists, the AI or the neural net people barely talk to any of them.
Well, talking to each other is one thing, but those things are highly formalized. The reason there is lambda calculus is because of the formality underneath, right? So the formality underneath is based on like hundreds of thousands of years of mathematical research, the same as for statistics. So then, if you want to blend these things, how would you want to go about it?
Yeah, that's the big question. And ultimately, all of this is trying to describe the one reality that we live in. And so these are sort of, I think of it as the elephant. You know, somebody feels the leg of the elephant, and they think, oh, elephants are these like a tree trunk. Another guy has the tail of the elephant. Oh, an elephant is like a whip, you know. And ultimately, there's a deeper reality that I think all of these are wonderful components of. And that some people tend to think like, oh, my way is right and everything else is garbage. I believe that actually we need synthesis.
Well, again, is it possible to have a synthesis? Like if you talk about elephant, like pretty much, I think what you're describing that in metaphor, it's multiple layered semantics, right? And you can have thousands of those layers of semantics and still not come to the concept of elephant, right?
Yeah.
It could be seen from many perspectives. So then, I'm not sure.
Yeah, I think it's a very interesting question. I have some things, but not ready to talk about it yet. So, yeah.
So, what's your insights of the current deep neural networks and based on limitations, you see there are some problems they couldn't solve?
Well, it feels to me like, it was basically 2 to 3 years ago when they started getting on the radar screen. That's when the investment came in. That's when all these papers or articles came out. Suddenly, everybody and their brother wants to learn about them. And the nice thing about them is it's pretty easy to take a deep learning neural net and apply it to something. So like if you look at Stanford has some wonderful online courses, video courses. There's one on natural language and deep learning that's created by Richard Socher, excellent lecturer. And I forget, there may be 200 students or something. They had a class project. You go look at their class projects. There are about 100 of these class projects, all out there. It's all freely available. They're amazing. Every one of these projects would have been a major research problem 10 years ago. And here, students in a 1-semester class who just learned about it, I'm going to use deep learning and make bot chorales. I'm going to train it on bot chorales and see what it does. Pretty good. Another person, there's an Irish jig. It's a kind of music. There's a website called the Infinite Irish Jig Generator. You go to this, and every time you visit the website, it on the fly composes a new Irish jig for you. And you listen to it, and it's kind of good, It's like, whoa. What's shocking is that you can basically take these things and apply them to anything and get something. And people are exploring more and more. Well, how many layers do you need? Well, how hefty should my computer be? And so I think we're in that exploratory explosion right now, where it's not at all clear where it's going to end up, but it's looking like nobody seems to find hard limits, like, oh, it can never do this. It's like anything anybody tries, it's like, eventually a few people will try new things and suddenly it's doing really well. So it seems like we're in that era where the future is very bright. Yeah?
So comments about other algorithms that could be used with, like, let's say the deep net is the eyes and ears of the control systems on top of that. Kind of like a Bayesian net, where you might have an attorney arguing for and an attorney arguing against. Or like you're doing detective work. You don't want to run something computational against the whole data lake. Maybe you want to focus it on a certain area size trial. And then focus the deep net on doing some kind of intrusion diagnosis or something like that.
Yeah, the Bayesian nets is a really interesting thing because so the deep nets, as I've spoken about them, they don't have an a priori semantics.
Right.
Whereas Bayes nets are actually manipulating probabilities of things.
So if you're like thinking about yourself, then you could make some assertions, what if?
And if you're a CSI detective, trying to agglomerate data, I've got evidence for this and this, or I'm an attorney, I've got evidence here. You really want that to be precise semantics if you're going to make a judgment based on it. And so exactly how there are deep analogs of Bayes nets that people have explored, they tend to be more expensive. Bayes nets is a pretty expensive algorithm, especially for big ones. And so how you exactly merge, the kind of good properties of this, good computational properties of this, with the more semantic properties of base nets, I think is a really interesting research area. Yeah.
How do you think the small companies and the startups compete with bigger companies? Because deep learning definitely need a lot of data and a huge computer resource. That's which small companies is short of.
Yeah, if you're like head on with one of the biggies, like let's say you want to make a new search engine and do your own little deep learning in your basement, probably you're not going to be able to compete with Google. Google has the resources, they got the data that probably you can't do. But if you pick a particular niche, let's say you love Irish jigs, you could probably make the best Irish jig maker, and no other company is that's not their niche. And so the good thing is that pretty powerful, sophisticated things can easily run on a home hardware, say with maybe one or a few graphics processors. So I think a little startup who has a unique niche can use these technologies pretty much out of the box. They're not going to be able to compete with the big guys on compute power, on data set size, but on what niche they have and what their business model is. I think there's a lot of opportunity there. Yeah.
For a person like me who know a little about this area, can you show me a pathway of learning the concept theory while mastering the programming so that one day I can apply it?
Yeah.
And I need shorten that's the procedure.
Yeah. Fortunately, there are some really good blogs, and if you just search on deep learning, like the one I mentioned, the Carpete, his blog is great, and they often have lists of free, totally open source software. If you use Python is a pretty good programming language, and they've got libraries to do all this stuff. And some of those libraries will run on graphics processors, and so you can actually get real compute power. And it's to the point now where you don't actually have to even really understand them very well to use them. There are a bunch of textbooks. People are writing textbooks. Joshua Bengio is one of the founders of this whole field. He's got a textbook, and the whole textbook is online right now as he's writing it. He's still missing a few chapters, but you can read that. These online courses at Stanford, I think there are 3 separate courses I found that are teaching deep learning, and they're all pretty good. And they have a lot of references to software tools to use. So the resources are there, and people seem to be making most of the stuff freely available. Sort of amazing, since in some sense this could be very strong competitive advantage, and yet Google researchers are writing tons of papers on how we did our FaceNet thing. And so fortunately we're in an era in which you can see what everybody else is doing and build on top of that. Yeah.
So what do you think of this robotics business? I mean, do you think we have all the technologies for the robotics to really have kind of similar functionality of human?
Well, I mean, I think you have to look at where. Like today, robots are still mostly in very carefully defined environments. So industrial robotics is great because you know exactly where the parts are, you know exactly what you have to do, and you just do it. In the home, the first big robot was Roomba. That's this little vacuum cleaner that, if it makes a mistake, it doesn't matter that much. There's starting to be like robots that are chefs. There's a robot chef that copies how the best chefs make their meal. That's not yet a consumer thing. One of the issues about robots is if they mess up, they can kill you. And you don't want to be next to an industrial robot because if it wants to move from here to the other side of you, it'll go right through you. And so very, very dangerous. And so there are some companies, there's something called Baxter, which has sensors on it and is trying to make it so that if it bumps into something, it won't keep going through it. So robotics, and then self-driving cars is a form of robot, and those seem to be ready for. We'll see. When the first self-driving car kills somebody, it'll be interesting to see what happens there. I don't quite know how society is going to respond.
There are actually some accidents Google cars have been.
Yeah, there have been some minor accidents. I've heard most of them are
kind of people like, what is that, slamming into the self-driving car. But,
and from AI point of view, I mean, think about it, a car driving on a highway, is it difficult to tell if a plastic bag is a rock or a plastic bag, for example?
Yeah.
If they will overreact to that, then what?
They try and be conservative, and I've heard that like some bicyclists, when they're riding, like when they're stopped at a stoplight, they don't want to put their legs down on the ground, so they stay on the bicycle, but they'll fall over, so they go forward and backward. And apparently the self-driving car is a little confused, like, is the guy going or not? And so there's been cases where the car just sits there not doing anything. But I think they want to go on the side of caution.
And the legalese is a lot more complicated, I think, than the technology in this case.
Yeah, exactly. Yeah, huge legal issues. Oh yeah, the legal profession, AI coming in a massive way. Just even evidence discovery, huge industry right now. And young lawyers are scared to death that much of what they do, contract writing and stuff like that, is going to be replaced by AI systems very soon. Yeah.
So do you think some, like ABB, they will put a sensor right next to the robot because somebody got killed in the Volkswagen factory, and the investigation report show was the human being fault. He walked into the operation area, so the robot doesn't know he's a human being now, he's a car.
Yeah.
So the robot just solder him, right?
Yeah.
Like a car.
Yeah.
That's why he got killed.
Yeah.
It's his mistake.
Yeah. Well, that shows that today's factory systems are pretty stupid. Like, it doesn't know the difference between the thing it's supposed to solder and the human. Bad, So pretty soon, hopefully, we'll get that level of semantics. The next level of like, what is actual ethical behavior? Huge discussions going on right now. There's a big letter on, autonomous military robots that have lethal force should be banned, like landmines are banned. Some people say it's a good idea, some people say not. So we've got big ethical questions about what role do we want these things to play? And exactly how can we be sure if we start putting them, like if you want the robot to like watch your child as a robot nanny, do you trust it? And then how can you be sure that it's safe? So big issues there. Yeah.
So right now we're doing all this stuff with 100-watt CPUs that are emulating nanowatt neurons, right? So there's a few places that are working on chips that do this more directly, like IBM working on it, I think there's a couple places in the UK and Germany. Do you have any view on that and how that might accelerate?
Well, I think there's a big difference between the cost of learning and the cost of executing. And so today, learning is really expensive because you need big data sets and you've got to crank through it. But once you've learned a model, there are often ways to compress it and get it to fit on a little thing. And so I have a feeling that that'll be a thing that you have. And like even today, like I have an Amazon Echo, which is a little cylinder that you can talk to and it'll play music and do other stuff for you. It's actually pretty good. And the way it works is it has some processing locally, but for anything difficult, it sends it back to Amazon. Now you have privacy issues, like how much is being sent back to Amazon? And then Facebook also just recently developed this system called M, I think it's called, that it's kind of a mix of AI and people, where you can ask it to do things for you, like order some flowers, or get tickets to the Mets, or whatever. And if the AI knows how to do it, the AI will do it. And if it doesn't, it'll get a person to do it, and then it'll train on what the person did. And so I think we're going to have that kind of thing where it's sort of a mix of complicated things sort of offloaded to humans, and simple things being done more and more by the AI.
So what was the name of that system?
I think it's called M. Has anybody tried it? I think it's live, and I think you can use it. I've seen a few. I haven't tried it, but I've seen some. M? Facebook M?
A-M?
I think it's just the letter M. Like for Messenger, except it's a sort of smart messenger. It's sort of like there was a company called Magic, I think it was, that you could ask anything. That one was totally human. You could ask it for anything. I'm hungry for pizza, and a pizza would show up. And I think it's sort of based on that, but with more. Like this one, I think you can ask it, what's the population in Norway and stuff like that. Yeah.
So for startups who are trying to take advantage of the AI, would AI as a service from like Watson be a good place to start and then try to see what applications to create rather than trying to create the AI itself?
Well, so it's a tricky thing because a startup, has very limited resources, and you have to figure out what is your competitive advantage. Whether Watson is a particular take on things that IBM is promoting. It's probably going to be pretty expensive, I would think. I don't know what their pricing is. And these systems are a lot of them are open source. So trading off, like, do you want to outsource it to somebody else who has expertise, or do you want to develop some internal expertise? I think that's a business decision. Yeah.
Just a brainstorm on pooling the nets. I wonder out loud if you could train the net to recognize an output that I've had dense training data here, or I haven't had training data here, so I have low confidence. And so that way, if it's outputting something like turn right, turn left in areas it's confident, you'll have this other confidence output. And if you're wandering into areas that it's never seen before, then you can have some kind of rule on top of it saying, let's not pay attention to this output.
Yeah, I think that's really good to have a kind of the beginning of a self-model, knowing what I know, basically. And there's something called active learning, which is if you have an area that you don't know much about or you're uncertain about, maybe you want more training examples in there. And so you can actually spend some resources to go get it. And that's a form of meta learning.
Yeah, but I'm saying, there's probably large areas you don't want to train in by all the common course.
Yeah. If you never need it, then you shouldn't waste any time learning.
Typically that is done in a neural network by just adding one extra layer, for example, and we just decide whether yes, you are confident with like 99% confidence or under 99%, so then you just add an extra layer that decides.
Yeah, you could definitely try that. Or you might want a whole other system which watches the system. If you look at the human brain seems to have we have a lot of kind of modules that look at other modules and make models and so on. That's an example. I think that's a really interesting research direction. I would say the answer is not clear at this point. Yeah. Yes?
It's a general question. So you mentioned logic in the beginning. So nowadays the learning-based approach is pretty popular. So what do you think the role of logic or the use of logic?
So far, the learning systems aren't doing much reasoning. Logic, gives you mathematical precision. Logic lets you do things. There are some attempts at doing learning logic, something called inductive logic. Those didn't really do really well. Our whole relationship with logic is kind of like Prolog was very, very exciting, and lots of people were interested. It's kind of faded. These days, most people don't use it. So I actually am a big believer in logic. I think it will be very important. But I would say it's sort of on the downswing at the moment.
And the problem with the logic is that it assumes that kind of a closed system, right? So this one is not necessarily based on facts, right? So
exactly.
Don't include the extra facts. Then
yeah. This system, something new comes, you get a new word. All right, well, I'll adapt to it, sure. Logic, a new word, what is that? It doesn't fit into the model at all. And so there needs to be some new kinds of structures that are kind of intermediate between those two, I believe. Yeah?
Have you ever thought about combining those two approaches?
Oh yeah, I do a lot of work in that.
Oh yeah?
Got some interesting things, not ready to talk about it yet, though, unfortunately.
Okay.
So, yeah.
What's the definition of intelligence? Because abstractly, I thought it was computing versus memory. But computer have a faster computation than human, and cloud computer have a larger memory than human. But why we still haven't yet generated a small robot that could active or stand running like human?
Yeah.
So what's the point?
So my own definition is that intelligence is the ability to solve problems. So you got something you want done, run from here to there, and it figures out how to do it. That, I think, is pretty clear. We're beginning to kind of, as this technology gets better, you'll see more and more of that. Humans, what we say is intelligent, we have things like wisdom, we have the ability to write poetry, we have painters who create aesthetic things, we have a sense of consciousness, we have qualia, the feeling of the color red and the sound of music and so on. All of those things, we don't yet have a good model of what those even are.
Yeah.
So it's not at all clear that these AI systems are going to have those aspects. And maybe maybe humans will stick with that stuff. Let the robots do the jobs that we don't want to do. I mean, anything a robot can do you really want to be doing that?
That's amazing. I thought the future is more like robot and AI could do a lot of things that they outperform human in physical ability. But in terms of feeling, emotional, and those kind of things, they are high dimension, in a completely different level of complexity than those physical laws. So that's the reason we're still far from the point that we worry that robot will drive human being out of existence.
Yeah, maybe. I don't know. We'll see. There are a number of companies trying to make emotional robots. There's a thing called Pepper that tries to respond to you emotionally. And some of the like Siri-like systems are now starting to try and understand human emotions. Whether we like that, whether we want that, I would say, we'll see. Probably in the next few years we'll see if we like this or not.
But you mentioned in the assembly line for those lower kind of labor-intensive jobs, lots of people will be deprived of their jobs by the robots. How people thinking about that? Because that happened quickly.
That will happen quickly. And I think as a society, we've got to deal with that issue. One idea that many people are promoting is something like the idea of universal basic income, where one vision of that is that all of this automation and robotics, that really isn't the creation of any particular person. It's really the whole of humanity that's doing that. So maybe the wealth, the extra increase of value that these robots are creating, maybe that can support the people who are not able to work anymore. I don't know. Big social questions.
That's socialism.
It's a kind but it's a kind of robot communism.
Oh my God.
So here's a way to think of it. It's not. There's a book called Mana. I don't know if you know that, by Marshall Brain, in which he examines exactly this issue. The story has two parts. The first part is basically humans get pushed into worse and worse jobs, and they are forced to work more and more hours, and then they're marginal. They can't do anything really bad. The second one, every citizen owns shares in the basically robot economy. And so as the robot economy does well, you get dividends. So that's a sort of more...
When robots learns to be adaptive, to improve themselves or evolve themselves, then I worry how I tutor or educate my grandson. Because 10 years from now, what's education should be?
Yeah, big questions.
For my son.
Yeah, the big problem is robots are not going to buy stuff. So how the manufacturers going to sell their stuff? Who are they going to sell to?
Well, they're not going to buy B2C things, but B2B. Robots are absolutely in B2B. There's a new technology called Ethereum. I don't know if anybody's following that. It's an outgrowth of Bitcoin, which is a cryptocurrency, which enables what are called smart contracts, which are entities which live on a blockchain, which can buy money, buy things, spend money, receive money, run little businesses with no humans involved. And so it looks like we may very well have a whole economy of just robot-to-robot economies. And so where does that lead? And these things, like you say, they can be improving themselves faster and faster. The robot economy may take off in ways that the humans are not even aware of.
Well, in that case, the robots are even going to take over the CEO positions and
yeah, certainly. Some people these days are saying that the white collar may be even more vulnerable than the blue collar.
Do you have any top 10 predictions for the next 5 years, or something? What are the milestones that you think are really significant?
Well, I think that list that I gave at the beginning of the areas that are going to be the highest value. That's where the money's going to go, because there's the highest possibility. It looks like automating business processes is the one that's going to. Current companies are pretty inefficient in many ways, and so better sensing of what is actually going on in the economy, better decision making, and better action. I think that's going to be the big economic driver. On the social end, I think we're going to see a plethora of robots. Everybody's using drones. You can get a $50 drone with a camera now. That's mind-boggling. And so I think we're just going to see an explosion of little devices. And where it goes socially is not very clear to me, but I think economically you can see the outcomes. Yeah.
I work for a small company. We only have 100,000 customers. So for that small size data, how we use this deep learning algorithm? For example, whether it's possible we can using other public available data to train the algorithm so that the structural algorithm is there, and then we can use that to fit our limited amount of data. How we use for
well, you can definitely model business processes, right? And there's things. There's the internal aspects of the company, and then there's the customer-facing marketing. using this kind of stuff for marketing. Like one of the huge advances in marketing was A/B testing, which is you don't know, like I have two possible ways of marketing something. Used to be some marketing director would say, yeah, I like this one better. Now you create both of them, you put them out on different web pages, you see which one gets more hits, and then you get rid of the other one. And so you adaptively change your marketing to better fit your customer needs. And so that kind of thing is going to happen in every stage in business.
I think there's something called embedding. You can train a different model with different data and then fitting your small set of data to that embedding system. And generate the embedding, then you use the softmax or another neural network for that and to train your own model. So basically you train a complex model with the big data and then use the complex model to generate the vector for your small data set.
Yeah. Right. All right. Well, thank you so much. It's been a good discussion. One more question? Yeah.
What do you see like statistical methods outperforming on getting like a language understanding of symbolic methods? Because like Siri-like application, there is nothing like machine learning is a little bit right, but it's rule-based. When you think of the tasks which are presented to deep learning, we're just getting a little bit better sentiment, but sentiment is like bullshit. The most reductionist approach for language understanding. In patterns, dialogue system, information extraction system, we cannot see big progress. Like Stanford parser, after 2 years of research, 1.4 better accuracies when symbolic system had 10% better accuracies. Because like 3 years ago, machine learning would change the language, and we companies in that were saying machine learning is slowing down our industry. And now the voices of deep learning is slowing down the industry of language understanding because we get fancy key plus something. But real effects, where can you see real effects in language understanding? I mean, symbolic or statistical approaches.
Well, I mean, I think we're in the zone when it's not clear what's really going to win. That the deep learning stuff seems to be able to do things that nobody could do in other ways. And so I think there's a lot of money and effort going into that. And I don't know if that's going to hit a brick wall or not. And meanwhile, I think there are some value to the symbolic approaches, which the deep learning stuff will have a lot of difficulty capturing. Though they're trying to do deep Turing machines. I don't know if you've seen that. And so it'll be interesting. I believe that a synthesis is really where things have to go. But that's more of an intuition than based on any...
Some people are commenting this progress in vision is the progress in animal AI. And some people say Google car is animal AI. My horse can do that.
Yeah.
My dogs recognize a cat, whatever it looks like. But grammar, only 3 to 4 years try to understand the language. And we are so far away from a human simulation. And we have great animal AIs working.
Yeah.
And pattern recognition, face recognition, is beautiful animal AI.
Yeah, exactly. One thing that's surprising is that the deep learning systems are very good at translation.
Yes.
I thought translation would require understanding of the world. But it appears that they can do a pretty good job.
They have the best sample in the world. They have so much text translated by humans. So it's more like statistical magic of human translation.
Yeah.
So it's funny to call it translation the way. And it reached the plateau. And now the plateau is like, we cannot progress.
Yeah.
So you think mixture of the systems.
Well, and what I have not seen in the deep learning stuff is much reasoning. These systems are not really thinking about things. And so I don't know if that's intrinsic or just nobody's really worked on that yet.
It's by design. A system like this is not really thinking, right? It's just generating some tasks.
Well, but partly that's the low-hanging fruit. Like right now, if you can just recognize what somebody's asking, that's a huge value thing. And so really understanding, their subtle models of the world, that fruit is a little higher hanging economically. And so
recognizing these as classification problems, not a thinking problem.
Exactly, right. So I think that there's a lot of pressure right now on the classification kind of stuff. But translation is sort of in that middle zone.
And translation, I think it works maybe from English to French because they have similar structure. But if you try to translate statistically from English to Chinese, I would bet $100 that I don't think it's going to work. Right?
Oh, that'd be interesting. I know Baidu has an English-Chinese thing. I don't know how good it is. But yeah.
So great. Thank you so much for the dissertation today, and Steve, thanks for a great talk. We definitely have to have you come back.
Thank you.